It's 1 minute before 10. Okay. So someone arriving late, someone arriving right at 10. Here's the first page. Many students, myself included, we don't have classes on Friday, but I know other departments schedule a lot of classes on Friday. So anyways, now you know. Therefore, there'll be no SI meeting on Friday, okay, of this week. Okay, it is 10 o'clock. So this is about arrays, the lecture material, especially in BSS segment. And here's one I just created out of thin air. And the name, the name is a number. The name, it's cost holds. Even more specifically, it holds the address of cell 0 of the array. Okay, so it is common that programmers move the name of the array into a register. This is common. I want to use the same name I used previously. Just for consistency. Do with that. Okay, I used R12. So just still move R12, comma, cost. So it's moving the 64-bit address of cell 0 into R12. And logically, we can actually say that R12 is the array. Okay, so your assignment number 2 is related to all this. Assignment 2 asks you to make 3 or 4 functions, one of which is input array, meaning input the values into an array. So this array is declared in a higher function who calls the one called input array. I think it looks something like, to be brief, it looks like manager calls input array. And manager owns input array. It's declared in the BSS segment of manager, declared here. And the array is passed like through a function parameter to input array, and input array gets numbers from the keyboard and puts them into the array. That's what we want to do right this coming hour. Okay, so here's the prototype of it, of input array. And it should be long. input array, parentheses, double one. No, that's C++ language for this function called input array. It's good documentation to put in your own program as a comment. This is what the function's prototype looks like. It's going to receive one array, and it's going to receive a long integer, which is the size of that one array. It'd be this number back here. That would be the second parameter. And the first parameter will be the number held inside of cost. Okay, that's how C++ would write it. We're going to do it in assembly right now, and you're all going to record it, and you're not going to harass your SI leaders to death how to make input array, because you already know. Okay, so this. Got one preliminary that's needed along the way. Okay, see how this a view of memory. There's stuff out here. Think of each cell of the array. This is cell 0, cell 1, cell 2, cell 3, and so on, out to the 19th, dot, 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 dot. 19th cell is the last one. Yeah. And then those are index numbers, 0, 1, 2, 3, up to 19. They're not addresses. Get a different color here. Each cell is 8 bytes, so I can't draw them that small, but there's 8 of these inside of here. Each one of those has its own address number. A, D, D, R, E, S, S. Yeah. So there's 2 numbering systems in effect. The cell counting numbering system, and then the byte counting system that's part of RAM, part of the machine's memory. Okay. Now, we want a way to, given an index, how do we get an address? And there's a nice little trick for that. And that's what this is about right now. Okay, so this is the array. What did we agree to call this? We haven't given a name yet. Okay. Here it is. Can you see that? Right there. Then the name, it has 2 names now. Cost, which we tend to disregard, and R12. So R12 plus 8 times, we need the index register. What did I use before? We'll use the next one. R13 plus 3. That's 1 byte. It starts here, and well, we don't know what's in R13. Let's say it's a 3. So in the picture, we go across here, cell 0, cell 1, cell 2, cell 3, and then count off first, second, and third, and I'll trace it out in dark black. There's 1 byte. How do you get the underlying address that 1 byte occupies in memory? Fortunately, there's an instruction that does the whole thing for us. And it looks like this. Okay, what I'm going to show you right now, what's coming, we really don't need the +3. We're just going to pick up the address of the first byte in the cell. Like this would be the first byte in cell 4. So we'd be more interested in LEA R8 R12 plus 8 times R13. Okay. The second number is a 0. So it looks like this. Again, what it does is uses the index here to pick a specific cell, like 3, and then this is focused on that 1 byte of that cell. So then this says, what is that address? And it puts the address here. Okay. You're going to see that this gets used in the next 20 minutes. LEA is the instruction. Okay. I have a diagram. I don't know if this, uh, let's go on. Uh, let's go on. Okay. So we're creating the function um, input array. Input array. It receives 2 integers. It is RDI RSI is the size. In our example, this is a 20. And it returns number of values entered into the array, or number of, it may be less, and it commonly is less than the full 20 values in array. Okay, you ready? So we start. Okay, segment text, segment input array. Oh, that far. And then I'm not going to draw right. I'm at 20 pushes, not 20, 16. I'm thinking of the size of the array. Can you read that? 16 pushes. Okay. Now, 2 input values came in under the name of registers that tend to be volatile. They tend to change a lot. Let's save them in a safer place. Or, oh, well, let's use the same ones that I was using before. R12. move R12, comma, RDI. And R13, RSI. And it's not a requirement of programming in this class, but you might document next to it what R12 is so you don't forget. R12 is the array. R13 is number of cells in that array. And we still need an index starting at 0. X, let's do this one. Next one available is R14. R14 is the usual index. I can't read that. Okay, we're going to loop this and watch. There's going to be 2 exits from the loop. And we'll start here. Okay, so let's give it a name here. Top of loop. The first thing that could go wrong, the first thing we're going to check for is R14 surpassed R13? R13 is the limit. R14 starts at 0 because of this statement here. If R14 is equal to or greater than R13, the array is full. R14. That's a 14, comma, R13. Okay. R14 starts at 0, 1, 2, 3, 4, and on. If it reaches 19, because indexing goes 0 to 19. If it goes beyond 19, we're in trouble. So jump equal, greater or equal. Okay, if it passed that test, then it says there's room in the array. We're going to set up a scanf call. So this is a block inside the body of the loop. One, load, and place it in the array. Place it in the array. So it's on tweak. Oh, I need to tweak. Think about scanf. You did that before, I think so. First thing we're going to say is there's no scanf inputs float numbers as if they were just a bunch of bits, thinking they're integers, but they're not. So it's kind of strange, but this gets a 0. Move RAX 0. It's the way scanf works, I should say. Okay, let's move RDI, the standard float format. And now scanf wants a pointer to the second parameter. A pointer is another way of saying it wants an address. What address does it want? There we go. Okay, it wants it in RSI. RSI, comma, square brackets of, name of the array is R12 plus 8 times, what's our index? 14. Scanf doesn't want an index counter. It wants a true, genuine address. So this references the start of the cell where we want the new number to go. So its index is in here, but that's not what scanf wants. Scanf wants a real address. So this gets it, and that's the second input parameter for every function call using integers is RSI, and I think it's ready to go. Call scanf, and then scanf receives either a number from the keyboard or it receives a control D. The instructions, your prompt should say something to that effect. Please enter a floating point number, or if finished, enter a control in a D. Let's test for the control D first. When you give scanf a control D, the low half of RAX changes to -1. The low half is called EAX. Okay, that's scanf's emergency mechanism. Something's going wrong. The user has given me a end of transmission signal. So it places -1 in EAX. Our program comes back and checks that. And if it finds they're true, the user is done. Jump if they're equal to out of loop. Now, in your ordinary programming, you should never use an E register just because I don't like them. But this is allowed. This is one of those, I think there's 2 other cases the whole semester where you can use an E register. This one is allowed and approved. Okay. If this fails the comparison test, then we have a number has been placed into the array at the location index stored in R14. And so it's time to increase R14 for the next iteration of the loop. They're going to put the next number will go into an increased R14. Okay, so after that, we do a J M P top of loop. Looks like that. And then loop that's the bottom of the loop there. So let's go here and we'll say, what do we call this? This is called out of loop. With a dot. Okay, I think we're pretty good here. No questions so far? Okay.
CMP's compare.
What happened?
CMP is a compare operator.
Is a compare operator for integers only.
Okay.
Compares one integer with another integer. Okay. When we get out of the loop, remember the prototype? we're working. The prototype is here. It says you have to return a long integer. And we should check the count, but I'm pretty sure R14 is it. So move RAX R14. It's a fact of function calling. If it's returning an integer type variable, it has to go through RAX to get back to the caller. But our count number is in R14, so R14 gets placed over there. And then there's a big block of 16 pushes, pops, actually. And then there's an RET. Okay. Now, perhaps you've noticed in your assignment 1, among these pops, there is no RAX. It's intentionally omitted for exactly this case. RAX has to hold the value that counts the number of values put into the array. It'll be a number between, it could be 0, and it could be 20, I think. Okay, I'm sure. But whatever it is, it has to go here because that's the universal passing back register for all integer data. If RAX was in here, one of the pops, then you put your good number in here, then it's going to be lost before it can get returned. And if it doesn't work, but if you had tried to put it here, move RAX R14. You're trying to put the good number R14 into RAX. If you put it down here, R14 has already lost it with one of these pops before that. So just moving this statement below the pops doesn't help either. The only answer is there's no RAX in the pushes or the pops. Intentionally, you never include that one. You've probably seen by now that RAX is used as a junk collector sometimes. If you want to get some stuff off the stack, the common thing to do is to pop RAX and throw it away. Pop it and throw it away. It's multi-purpose register. Multi-purpose. Okay, that's the end of the story. What does the clock say? We did that in a half an hour. That's pretty good. Okay. No, I don't know. It's kind of out of style to teach with diagrams. Faculty don't do that usually. Here's what it looked like before I wrote the code. This is a diagram. This says up here, input array. And so on. Okay. Execution flows forward. 16 push. And then came 3 operations that have to be specified individually. Or, let me make sure I'm not changing the letters. Okay. R12 gets RDI, R13 gets RSI, and R14 gets zeroed out. Then use a diamond shape thing. You're checking to see is R13 greater than or equal to R15. If the answer is yes, execution flows over here and turns the corner and goes down. If it says no, execution goes down here. And I think in the old days, there was a double side meant calling a function of some kind. So here's a setup scanf. And then diamond means you have to make a decision, if then else. And then you're checking to see if EAX equals -1. It's hard to read it, but if the answer is yes, this line goes over here and meets that one. If the answer is no, then increment R, what was our number? 14. And after which, everything is still good. Execution flows to here. Then this one flows to RAX, receives, let me make sure we're using, I think it's R14 is the counter index, R14. Make sure. Yeah, it's the zero down. After which is 16 hops. And after that, the function ends. So it was a kind of oval used to say this is an off-page connector. This is the return. Okay. So without any code knowledge, without reading stuff, you can see it in an eye scan what's happening, where the program's going to execute. There's actually two exits. There's an exit from the loop. There's an exit here when you're overflowing the amount of data in the array. You can get out, or if you discover that the user has input a control D, you join this one and you still get out. Okay. A couple of years ago, the administration sent a memo around that said, don't teach flow of control in diagrams. So I don't know if that's anyone paid attention to that or not, but there it is for whatever it's worth. It does tell a story that's easy to understand in pictures that doesn't require reading a bunch of code. Okay, that was the main lecture. So where does this all fit in? That, okay, see if I can remember it. I can't remember this. Assignment 2. There's a diagram. Main. And then there's an assembly function who doesn't get involved very much with details. This is a higher level chief technology officer, higher than the details. Then this one gets involved with name. I don't remember the name I gave to it, but I'll call it manager. And then this one in turn calls input array. And it in turn calls sort the array. And at a different point in time, it calls, I think it was the sum of numbers. And at another point in time, it calls output array. My marker is new and it gets too much ink out at one time. Output array and the sum of numbers in the array and the sort of the array and the input array. So right here on this Monday, you saw all about this one. Now, part of this is practice passing data. You're learning arrays and you're passing data back and forth. Every sort that I know of, except radix sort or there's one or something, they all have a point where they swap two values. Okay. So we're going to put that in. I think this was C language, and then swap is an independent function. Very short. It receives two numbers and it swaps their position, where they're held. In technical terms, they switch position and the first one receives the second one in its address, and the second one receives the value of the first one in its address. Okay, so that's assembly x86. Yeah, most of this is assembly. Okay, because I know you're already experts in C++. I want to see your assembly code. I think that's the diagram. 1, 2, 3, 4, 5, 6, 7, 7. Is that right? 4, 5, 6, 7. 7 functions. It's really it's truly partitioned. Okay. When you leave the team or the team concludes their project, some maintenance group will come along and upgrade the program every year or every 6 months. You know, and it's if this was magnified, scaled upward, where there's 150 of these modules, and the maintenance team is requested to change the GUI and show a little man walking along the path in the jungle, all you have to do is find the one module that handles that, wherever it is, and you work on that. And the system is so well partitioned that it doesn't affect anything else. We have some here, but what if it was find the largest value? You could pick this out just like pulling a plug out of the wall socket. You put that out and you put the next one in there, and everything's good to go because it all interconnects by standard, what is CC? C calling convention. C meaning the language, calling convention. If all functions in the world adhere to that, they will call each other no matter who made them in any language. It wouldn't matter. And the calling convention is what we've been doing. RDI is first, RSI is second, RDX is third, RCX is next, R8, R9. After 6 integers being passed, any additional integers have to be on the stack. C++ and C and any language that compiles code will follow that calling convention. But it's not mandatory. Makers of compilers can set up a different order if they wanted to, or a different set of registers. But most compiler manufacturers of the world follow that standard convention, and we are too. Okay. Says he spotted a mistake, R15 or 15, 14 or 15. What is?
So when you were comparing R13.
Oh, this one? Oh, maybe so. Let's fix that before. $13 is index and the max size is no 14. Yeah. But let's fix this. It's index compared against the maximum number of cells. I would have liked to have written R14. Are you greater or equal to R13? So you play back the recording. This is supposed to be R14. That's the current count of numbers in the array. Are you greater than or equal to the number of values allowed in the array? R13. Thanks. I did. Yeah, it's only watching. R14. Yeah, that's right, R14. But R13. See, I had this back here. This is not required for your assignments. You don't have to document line by line unless you want to. There's nothing wrong. It helps. This helps because your mind will forget which one of these is doing which activity. So this is helpful even to the current programmer, much less one of the future. Okay, any questions other than this? Okay. So we finished 6 minutes early. What can we do for 6 minutes? Or 16 minutes. That's good. Yeah, I was trying to do this before class, but I didn't do it very well. What is this number? X. This is a puzzle. Okay. There's all math stuff. It isn't even computing. 401 is the stored exponent. You have to know it. 3FF is the bias number. You subtract, but you count on your fingers. Starting place is 3FF. Next number higher is 400. Next number higher is 401. It's a distance of 2. That's true exponent. So our number, I'll just call it n. There's a hidden bit, 1. And then there's F, 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 forever after. $52 ones times 2 to the 2. What it means is it's 1 plus a half to the 1 plus a half plus half. The whole thing times 2 to the 2. So I interpreted each one by position. And that's pretty good. Now, how do we get we want a decimal number out of that. Think of this for a moment. That 1 is really 1/2 to the 0. Plus all these other 1/2s. There's a whole bunch of them. In math class, you're supposed to write that as sigma. K equals 0 to 52. 1/2 to the K times 2 squared. Now, somewhere in the calculus book, in the exercises at the end of the chapter, that sigma is given a formula. This one. The formula is this. I'll rewrite it as the 1/2 is not important for the form. It would be to n of anything a raised to the k is a is something 3, 2, 1/2, 1/4, 2/3. It could be anything. So someone else has figured this all out. We want to use this one. In our case, The n is a 52, and the little a is a half. So it solves the puzzle. E is half to the 53 divided by 1 minus a half to we go as far as we can without using a calculator, then we stop. Okay. Well, the denominator can be cleaned up a little. The denominator is 1 minus a half is just a half. Upstairs, it's somewhat more complex. 1/2 to the 53 times 2. Okay. It's a compound fraction. You take the denominator, turn it upside down, and multiply by it. Well, this is a 4 and that's a 2. They could be combined as an 8. Let's see, 53. That's as close as we can get without electronic calculators to carry out this exponential term. So what is this? What we're looking at is 0x401 f a lot of f's. It's that number. But if this fraction raised to that gigantic exponent makes this value very, very close to 0. It's not 0. And this is true accuracy. But if you just rounded it off by covering that up, it says the number that we started with is pretty close to 8. What do you think of that? Okay. We're not out of time yet. It's not yet 11 o'clock. In the number line, there are numbers out here. Well, let's put 0, 0.0. And here's the positive side of the number line. And then you come to a certain point called infinity. And then there's a few numbers beyond that. So there's a marker here. And this is an open set like such. And then down here, there's a special number. What is its name? It doesn't have a name. It's the smallest normal number. Smallest. Sorry, you can't read my writing. Smallest normal number. Okay. Oh. This is the positive number line. The greatest number of values is here. Those are normal numbers, normal floats. These over here are called nans. And these in here are called subnormal numbers. They're very tiny. They're very close to zero, but they're real numbers that the computer works with. These out here are larger than infinity. The computer will reject them. Non-operable numbers. You can't. They will show up in your register sometime, but you can't multiply or add or subtract to them. So non-usable numbers. Okay. So your assignment is what is the hidden value of infinity? Okay. So to define infinity, its stored exponent is as large as you can make it. Stored exponent is maxed out. All stored exponents have 11 bits, and so this stored exponent would be 11 ones. And then, see, that's the dividing place. There's a dividing place between nans and normals. Then the nans also have that same max exponent, but infinity is the only one that has all zeros for mantissa. Okay. $52 zeros. So we can write this number in hex, IEEE style, 11 ones, but I can't write FFF. That would be 12 ones. Infinity is not negative. We have to have the first bit as 0 and then 1, 1, 1, 1, 11 times. That's 7FF. Okay. And then the definition says the mantissa part will be all zeros. That's it. That is in a computer, not in a math class. Okay. Now, if any one of these zeros just changes one bit, then it's not infinity, but it's in that group of nans. Um, you know what? I don't have enough zeros. You have to have 16 of these. I didn't count well back here. The grand total of digits is 16. So if there's one bit that changed someplace, and this is nan, and this is inf. Have you ever used printf and got a nan? It'll put out the letters NAN and not show you anything. Do a multiplication of two very large numbers, two very large float numbers, and it'll overflow, and then you'll get an AN, and printf will refuse to output it. Okay. So This is usually this is a homework assignment. How do you write infinity in decimal? Well, you start with that's not it. You start with the stored exponent and you subtract the bias number, 0, 0, and it's 400. Okay. And then the mantissa part, well, how do you translate that to decimal? That means 4, 1, 2, 3, 4, 1, 2, 3, 4. Whenever you have a 1 followed by some zeros, a lot of zeros or few zeros, it's always equal to 2 raised to the number of zeros. Did I have a count? Yeah. Okay. That's strange, but that's the way it works. There's a 4, 0, 0, 0. That's 10. 10 to 2 to the 10. Everybody knows what 2 to the 10 is, don't you? Every computer science major has that embossed on the back of their driver license. 2 to the 10 is called what? 1 kilo. 1 kilo. Kibibyte. Okay. All of our data traffic is measured in, see, kilometers is metric system. Okay. It's a little, I forgot it. I think it's little km, big M. Anyways, kilometers, that would be 1,000 meters. On data traffic, it's KIB. I think they pronounce it kibi bytes. It sounds so stupid, but that's what it is. Okay, so kibi bytes is 1024, which is 2 to the 10, which is involved with infinity somehow. Okay, so back to the subject. Infinity has a hidden bit, and then all these zeros times 2. By the way, that's stored exponent minus bias number is true exponent. True exponent is 1024. We're getting close. Mathematically, you simplify that and it says 24. And then we won the battle. That's what it is. Okay. Well, this is now open office hour time. I'll be here. It's my job to be here until about 15 minutes before 12. You do what's necessary for your education. And I'll be glad to talk to anybody in person or by chat messages, however, whatever's convenient. Okay, that's a neat number. 2 to the 1024. Oh, it gets the memory address.
Oh, this whole chunk going.
Oh, yeah, this whole chunk references 1 byte. If you were to multiply it all out,
So
it gets you to 1 byte.
which byte?
Oh. Okay, let me point out something. Here is cell number 3. Okay. This is the array plus 8 times the index 3 plus 3. So here would be 3 bytes over, about underneath my pencil there. That byte, the third one of the third cell, that address would be copied here.
Assuming the third cell is at R13.
Oh, yeah, I'm assuming R13 holds the value 3.
There's something that.
That would be true if we declare the array at R12.
Oh, yeah, the starting point is, that's independent. Here's R12.
Okay.
That's the address way out here.
The first byte,
Yes, the first byte. On the
and then
right side.
plus 8 is over 8 bytes.
But.
No,
I'm working backwards with this.
8 times whatever integers
Oh.
here, like 3, it'd be over 24. If this holding a 3, then it goes over 24 bytes and it ends up somewhere in the middle of the third cell.
And if R13 plus 3 is just like an example, right?
Yeah, this is a made up example.
And we would do that like in another line up ahead. Where we store 3 into R13.
Yeah, that's right. R13 have to receive its number from up above.
That'd be R12 plus 8 times 3 plus 3. That'd be 24 plus 3.
27.
27.
27 is the,
27 divided by 8 is 3. And
what is 27? 27 is the count of bytes from here, from the start on this edge.
part of an 8 is like
Well, it's 3 and a flat.
3 days. So I'd move over 3 and then go over 3.
3 bytes within this little cell
And
program.
then it would take that byte and copy it to R8.
Yeah, it's not, it's not.
It will take its underneath address.
I know, but.
See, addresses exist in RAM
It was
apart
just
from
like.
arrays.
So if we were to store like a number in this array, what do the bytes represent?
Okay.
Or is each byte a number?
Oh, no, there's 8 bytes in one of these boxes. You can load it up
That was
here.
like cryptic.
All quad words.
Well, what if we load a number into slot 0 and then what would each byte contain?
Oh, okay. Uh, I don't have one here, but you asked me. It's a messy thing. If you loaded in a number into, say, cell number 3, what you're getting there is 40497B 8 C 7D 1 2. I need 8 of these. 509D. Okay. There's 8 bytes here. 1 2 3 4.
Give the downloading.
Are
they
those
in camera?
examples? Or
Yeah, then you said, what happens if we load a number? That's the number. 6A. All float numbers end up looking like this, not like our decimal numbers. This is what the machine sees. So this is byte inside that cell 3. This is 0 byte 1 2 3.
that's taken from the hex to the decimal number to binary, use the bias number, and then hex, right?
Yes. We humans need to see it in decimal. The machine doesn't care. It just wants that.
So this is from the conversion we did last week, right?
Yeah, the conversion we did last week.
And then that number is split into 8 sections.
Yes, and so you